So welcome everyone. This is the third webinar in the series on graphene in collaboration between Europractice and the 2D-EPL, so the experimental pilot line of the graphene flagship. Today we have the third webinar. I said it's the focusing on the second 2D-EPL MPW run towards sensor CMOS integration by Miika from VTT. And let me first introduce Miika. So Miika is a senior scientist at VTT Technical Research Center of Finland. He obtained his master in science from Tampere University of Technology with major of biomeasurements and minors in industrial economy and biomedical engineering. He has 10 years of experience in graphene-based sensors, including biosensing, infrared detectors, gas sensors, focusing lately on wafer-level fabrication and sensor CMOS integration. So he's leading the 2D-EPL work package 3, which is focused on the wafer scale integration, and there he is the leader, as said. He is also the project manager for the 2D-EPL and EPL at VTT, and he's project manager at VTT for graphene and CMOS integration related customer projects. He's ongoing part-time PhD studies as well at Aalto University in the field of nanoelectronics. So having that said, I have introduced Miika. So Miika, the floor is yours, and let the people show what they can do in the second MPW run for graphene.
Oh, thanks a lot, Romano. So let's move ahead with the presentation. So the outline of the presentation, I will introduce VTT shortly. Then there's also a short introduction to the 2D experimental pilot line project. And then there is general fabrication steps for the CMOS integrated graphene sensors. And in the end, we have the MPW Run 2 introduction, including the baseline process, die designs, quality control protocols, and the timeline and the cost for the run. So about VTT shortly. So VTT is the Technical Research Center of Finland. We have locations all around Finland. So the largest location that we have is here in Espoo. That's close to the capital of Finland, Helsinki. And our microelectronics center is also located here. In the other sites, like in Oulu or in Tampere, we have, for example, printed electronics, where we also have like a printed electronics pilot line facilities. And then in Tampere, there's focusing on manufacturing industry and materials technology. And in addition to these major locations, we also have some smaller locations that are specialized in some particular research topics. For example, here in Turku, we have this autonomous systems team operating. A bit more about the Micronova research infrastructure, which is the Micro and Nanoelectronics Center here in Espoo. So we have about 2,600 square meters of clean room area. This facility is jointly operated by VTT and Aalto University, and it's meant for research and also for pilot scale production. In the we have also different characterization laboratories, as the Millilab, that is European Space Agency's external laboratory for millimeter wave tests and characterization up to 300 gigahertz. Then we have also quantum and cryogenic characterization laboratories and optics and photonics, and also sensor laboratories. Here you can see our facility here. Some office space on this side of the building, and then the clean room premises on the other side of the building. Something more about the Micronova infrastructure regarding the clean room capabilities. So we have lithography capabilities with the stepper and contact aligners, and also with the electron beam lithography. In the etching, we have several different options here for oxides, nitrides, metals, also HF vapor etching and Xen fluoride etching, also some ion beam trimming options, and also various wet etching options. In the deposition part, we have LPCVDs, PCVDs, ALDs, and also parylene deposition option. Then we can also perform ion implantations and also plating. We have plating options for several metals here. 3D integration side, we are capable of doing CMP for silicon and oxide wafers, and then there's some wafer bonding options and grinding and ion trimming. In the back end, we can also do some dicing, flip chip bonding and wire bonding, and we also have a pick and place tool option. The main technology platforms in Micronova are these 616 platforms here. We have active silicon devices, silicon photonics and integration, MEMS and MOEMS, and then also thin film RF components and integration. The quantum devices has been lately growing as well quite a lot. It seems to be quite a hot topic. And then we also have the main topic of today's presentation, which is the 2D material device and integration platform. Mainly for different kind of sensors and also integrated photonics and terahertz detection. Mainly focusing on wafer scale fabrication. Some examples that we have been studying on this area. Here we can see a few examples of the sensors that we have been fabricating. Here we have a biosensor device where there's a graphene channel here. Then we have done some passivation of the device and the channel opening to enable biomeasurements, and here there's source and drain electrodes. This device is liquid gated FET, so the gating is performed through the liquid that is placed on top of the device. Here we have an array of backgated graphene FETs that could be used, for example, for gas sensing or infrared sensing studies. The next level from these devices is the CMOS integrated devices, where we can have large sensor arrays integrated on top of the CMOS readout, which is also the focus of this presentation here. Here we can see similar biosensing devices as in the top image here, but just integrated on top of the CMOS readout circuits. Then we have also some activities with the optoelectronics and flexible electronics areas. With the optoelectronics, we are working with some waveguide integrated detectors and modulators, and here's one example of a flexible photodetector platform that we were working with in the past. So just a short introduction to the areas that are commonly considered the most promising for 2D materials. So we have here some application areas for both the graphene and also for the TMDCs for other 2D materials. For the graphene, the most promising areas are in the sensors and also in the RF electronics. There's some applications in the packaging, power devices, and NEMS and flexible electronics, where graphene has potential. But then the TMDCs are mainly considered to be useful in this logic applications and also for some cases in packaging power devices, NEMS and flexible electronics. And here we can also see which applications are coming first. So we can see that the sensors, these have already been possible to do some sensors with graphene for some time. And the next ones that are now appearing are the cameras and spectrometers, and then there will be also the modulators and detectors with graphene. Then the later part here, it's more related than to the other 2D materials. So for example, transistors and neuromorphic computing rely more on the DMDC based device. The interconnects can be also done with graphene. So then short introduction to the 2D experimental pilot line project. So it is a project inside the Graphene flagship. So it is it started in October 2020 and it will last 4 years. We have 20 million funding to achieve the goal to move from the chip scale manufacturing to the wafer scale manufacturing. And this includes making the 2D materials compatible with the industry standards, development of critical tools and chemistries and materials. And in the end, we hope that we have achieved to establishing a European ecosystem for the 2D material integration. The operation works also as a foundry service, so with these different MPW runs that we are offering. And in the end, we are also hoping that we can make a technology transfers to, for example, CMOS foundries that could then utilize the technology developed in the 2D-EPL directly for their customer offering. And how the 2D-EPL is structured, we have 2 different pillars here. In the pillar 1, we have already established technologies that we can utilize to offer services to customers already quite early in the project. So you can see it here. From the starting of the project, we have had an internal development run. Now there is a MPW run 1 open by AMO, and then we have further MPW runs along the project. So this is already possible with the polycrystalline CVD graphene on 200 millimeter wafers. But in the pillar 2, we are continuously developing more advanced materials and also automated tools to make this more compatible with the industry. And then we are also bringing up some more advanced modules for the photonics, electronics, and sensors. And how everything is organized in the project, we have 11 partners total from pretty much all around Europe. And in the first part, we have development of tools and materials where we have SÜSS MicroTech, Aixtron, MRT, Oxford Instruments, and Graphene. And SÜSS and Aixtron are providing us some advanced tools to enable the graphene transfer and also growth. And then MRT is providing us some custom resist to develop cleaner graphene processing. And Oxford is developing some ALD processes for the 2D materials, and Graphene is responsible for the graphene production here. In the module and platform development side, we have VTT, IMEC, AMO, and IHP. And then in the MPW runs, we have VTT, IMEC, and AMO. And everything is coordinated by Chalmers University of Technology. And then a bit more about the ongoing MPW runs. So the run 1 that is now open by AMO is focused on sensors. Then we have the second run coming right after the first one, which is organized by VTT. After that, there will be third run by AMO and again fourth run by VTT, which is then focused on the sensor CMOS integration. But to participate in the run number 4, it's highly recommended to test the process already in the run number 2. And in the end of the project, there's one run also by IMEC, which is focused on the TMDC-based transistors. And then let's move to the general fabrication steps for CMOS integrated graphene devices. The process at VTT has been usually like this. We have been doing the CMOS readout designs at VTT, and we have outsourced the actual CMOS readout wafer fabrication part. And then we have continued with some post-processing steps, for example, via etching, gate metal and gate dielectric depositions, graphene contact depositions. Then the graphene transfer part has been usually done by our project partner Graphene, and VTT has done then the graphene patterning and also the encapsulation and channel opening of the devices. Also, once more, so in the MPW run 2, we are utilizing gate, contact, graphene and encapsulation modules, and in addition to that, in the MPW run 4, excluding the CMOS fabrication part, we will have the via module there to contact the graphene devices to the CMOS readout that's underneath. So in the via module, we have the via etching, via filling. In the gate module, we have gate metallization and the gate dielectric deposition. In the bottom contact, we have are depositing the graphene contact metals. Then there's the graphene transfer and patterning step in the graphene module, and as a final steps, there's some passivation layers deposited, and the channel is opened for example, if you want to do some biosensing or gas sensing or infrared detectors, then you need to be able to access the graphene. So some application examples. The first one is what we have been working with at VTT. So we have been working on this kind of CMOS integrated biosensor arrays, and these have been done on so that we have been post-processing 200 millimeter CMOS wafers. The process here has been or the wafers have been fabricated at XFAB, and then we have done the post-processing steps at VTT. So similar to the process shown in the last slide, but excluding the bottom gate electrode under the graphene. So these devices were gated through the liquid electrode. So the liquid gate electrodes are shown here on the chip, and here you can see the vias. Then there has been some metallization to bring the contacts from the bottom of the via to the top, and then there has been source and drain electrodes connected to the graphene. Then the graphene area has been patterned here, and then the channel has been opened. So here on the right side, you can see some statistics from these kind of devices. So some resistance variation across this kind of chip with 512 graphene FETs, and here also as a function of the gate voltage, we can see that most of the devices are quite nicely packed in this area here, but about 5% of the devices have this slightly higher resistance levels. But in the end, as we can show these devices here, that when we are operating these as sensors, also the devices with the slightly higher resistance levels are behaving in similar manner when used in biosensing, or let's say here as a example, just for the sodium chloride concentration detection. And here's just some additional statistics from different chips. We can see that the resistance values are quite uniform for the different chips. Then another example where we could utilize the CMOS integrated sensing is in the gas sensing. If you were joining the last presentation by Gordon, you can maybe remember that he introduced the gas sensing possibilities. But if we would go for the CMOS integration, I think then it would be possible to combine several different functionalizations on same chip, and this would enable multi-analyte sensing, so in this kind of like electric nose type approach. And I think that's the main benefit in general for all the CMOS integrated sensors, is to have the multiplexing and then the multi-analyte sensing. Well, of course, there's the added benefit of the integrated readout electronics. And then another example is this infrared camera or the sphere camera applications. So this was also presented for a single device by Gordon last time. So if we would make this kind of like graphene FET cameras and functionalize those with quantum dot layers, we can then realize this kind of like Swiss sphere cameras that are, for example, being developed by Curve, that is a company based in Barcelona. There's chip from their production, and then also there's another company that's developing similar technology, which is Empyrean, and here's their camera module, which has this kind of technology included. So then if we go a bit more in the MPV Run 2 details, similar to the MPV Run 1, the applications are for these biogas chemical sensors, also Hall sensors or photodetectors. And it would be recommended to join this run if you are interested later to join the MPV Run number 4, where we are doing then the CMOS readout integrated sensors. In this run, we have the gate module, the contact module, then the graphene module, and then the encapsulation module included. The material is, or the substrates are silicon dioxide substrates on 200 millimeter wafers. The typical die size is 1 by 1 centimeter, but this can also be negotiated based on needs. The values that we are promising for these devices at the graphene mobilities will be over 1000, and then the seed resistance values will be around 1 kilo ohm when further away from the Dirac peak, and around the Dirac peak region it will be around 4 kilo ohm. And then the average contact resistance values will be around 1 kilo ohm micrometer or less. The minimum working devices are 80%, and then the Dirac point will be plus minus 10 volts, and then the safe gate source voltage for the process that we are working with is plus minus 30 volts. If you consider the difference to the MPV Run 4 that's then coming later, then there will be the VIA module added to these, and then the CMOS process underneath there will be, for example, XH018 by XFAB or some similar process. This is a process that we have been using for our test runs. So just some more statistics. So even though these are the values that we are promising, I think we can go up even a bit higher than that in our development runs. We have been able to achieve contact resistances with average contact resistances below 400 ohm micrometer, and with the standard deviation of 790 ohm micrometers, and also the doping values are already quite nice. This corresponds about minus 1 to 2 volts with 50 nanometer aluminum oxide gate dielectric, and also the mobility values are at the moment a bit over 2000, but I think we can still optimize this a bit more before the MPW run 2 is delivered. The layers in this process include the backgate, which in our process is titanium gold with the thin titanium adhesion layer and then 30 nanometer gold layer. The dielectric layer will be there's option to have either aluminum oxide or silicon dioxide. Thickness is 50 nanometer, and the bottom contact layer is similar to the backgate layer. There will be titanium gold there as well. The graphene is a single layer graphene, and in the encapsulation part we have the aluminum oxide and silicon nitride combination there. So the same here. So the details for the modules. The die design for this MPW run 2 will be similar to this one. There is a 1 by 1 centimeter chips and also some test structures included. So this part of the design can be then decided by the customer, and then we will include some test structures next to each chip to be able to monitor the process and the process uniformity. Typically, we have here different type sizes of FETs, then also some TLM structures and some capacitors. The design rules for this run are same as for the first run by AMO. So there's 5 micron critical dimensions for the alignment and also for the line widths. Shortly about the quality control and the standardization work. So the process has been started also in this regard together with the IAC and the Graphene Flagship Standardization Committee. So we are moving forward both in the material characterization side and also for the electrical analysis part. And hopefully this will be later available and utilized as standards in the industry. At the moment, we have a quality control for including Raman spectroscopy, AFM measurements, and optical measurements during the fabrication, and then most importantly, the electrical characterization, where we are monitoring the electrical parameters, just mobility, contact resistance, seat resistance, doping, and hysteresis of the devices. And then about the timelines, so this call will open 1st of July this year, and then it will close in the end of October. And then the actual run will happen from March to April next year. And the cost structure is targeted to be similar as in the MPW run 1, but we will still confirm this when the call is announced during the or by the end of or the start of July. So the costs for the run run 1 were like this. So 1,300 is the starting costs with 4 dies having this design. So and then each die, in addition to that, is 250 euros, and there's discount for certain partners. And short summary. So VTT is part of this 2D-EPL project, and we are offering the second and fourth MPW runs, which is mainly focusing on these biogas and chemical sensors, and also HALA sensors and photodetectors. And we went through the general fabrication and application of CMOS integrated graphene devices, and then the baseline process for the MPW run 2, and more information and the application to join the MPW runs can be found through these links. And shortly, just a reminder of the MPW run 2 modules that are included: the gate, contact, graphene, and encapsulation. And we are coming near to the end of our presentation, but just a reminder that you can find this and the previous webinars from YouTube. And one more reminder that if you are still interested, join the MPW Run 1 that is already open at the moment. You can apply to it before June 30. That's it. Thanks.